Okay, good morning, ladies and gentlemen. Thank you for inviting me to share some of our research concerning ring resonators today with you. So today I will talk about selective mode coupling in microring resonators. I will explain what that exactly means. My name is Amir Arbabi, and I work with Professor Linewidth at Photonics Systems Lab. So here's the outline of my talk. I will start by motivating you about what we are doing and why it is important. Then we'll give an introduction about Microring Resonators for those of you who are not familiar with these devices. In the next section, I will move to explaining simulation and design tools that we developed for simulation and also designing these devices. And specifically, I will talk about how we can find the resonance modes of these devices, also how we can use a coupled mode theory formulation to calculate the mode coupling in a ring resonator. I will talk about the fabrication of these devices and measurements, and at the end I will summarize my talk. So to motivate you about this research, our main work is on to making a better laser diodes. So laser diodes are semiconductor laser diodes are structures that have an active section, and usually they have two mirrors. So similar to any laser structure, you have an active section or gain medium, and I have two mirrors that create the feedback. For single mode laser diodes, usually have a selective mirror. In this case, we have a gain medium, which is active port, and a reflective mirror, which has a selective reflectivity. So as a function of wavelength, the reflectivity of this distributed Bragg reflector, which is just a periodic structure, but changing the index of the material, can make that. So the reflectivity of this structure looks something like this. So at some design wavelengths, you have a large reflectivity, and then there are these side lobes, which cause the side modes in the laser at the end. And so the laser wavelengths the laser will lay somewhere around this design wavelengths, and then we will get some side modes because of those small reflectivity peaks around the actual design wavelengths. So such a structure usually has a large footprint. To get a narrow enough full width half max for this reflection peak, we usually have to bright this for a few millimeter to even few centimeter. So it's a nanostructure with the period about 150 nanometer, but you have to write that for a few centimeters. The uniformity usually becomes an issue because you have to keep the period fixed, otherwise this reflection peak becomes wider. The other problem that I mentioned also are the noise in the laser output that you will get because of these side lobes in the reflection. They will cause side modes in the laser. So what we want to do is we want to replace that reflector, which is a distributed Bragg reflector, with a smaller device. It's a resonance device. So we have a ring resonator with some grading written on top of on the ring waveguide, and we expect to get from this structure we expect to get such a reflection peak, and this structure works based on coupling the degenerate modes of a resonator. And as you can see, you can get narrow reflection peaks. There's no side modes in this. So because the whole structure is pretty, also the whole structure is pretty small. It's in the order of less than 100 micron in size. And also when you want to tune the laser, usually you tune the wavelengths of this reflector. So when the reflector itself is small, we would need smaller powers, or its power to tune the structure. As I mentioned, there is no side modes in this structure. The other thing is the full width half max of this reflection peak does not depend on the length of the structure. For the DBR case, if you want a narrower reflection peak, you have to increase the length of the device, as I mentioned, to 2 centimeter. So here's this there's an introduction to these traveling wave resonators. That Microring resonator is one type of those. So in these traveling wave resonators, what you have is in the light end, and then the light is being trapped in a circular path. So in the ring resonator, you have a light trapped in a ring, so that light propagates along the ring. You can have these modes just in a microsphere. So if you make a microsphere, because of the total internal reflection, you can have light being trapped inside the sphere. They have also a form of these resonators. You can make a micro disk, and the light can be trapped along that. Also, if you reflow this micro ring, you can get micro disks. You can get micro toroids. So there are different designs of these traveling wave resonators. The main thing similar between these is that the light is trapped in a circular path. So we are mostly interested in Microring resonator. The main reason is that they can be fabricated on a chip. So we can fabricate a lot of these devices very close to each other. The fabrication can be controlled very well because top-down fabrication. So a ring resonator, as I mentioned, you can set the light, and the light is coupled to this resonator whenever this resonator has a resonance. And the resonance happens when the path length for the light is a multiple of the wavelengths of the light. So the fabricated device looks something like that. You have a ring, a bus waveguide, and the ring resonator is coupled to that. Normally, when you measure the transmission of this device, so how much light is transmitted through this device, we'll see dips in the transmission. Whenever the ring goes to resonance, the whole light goes and gets coupled to this ring resonator and gets lost inside that. So we get zeros in the transmission. The modes are uniformly spaced. Another important thing is that because this structure has circular symmetry, at each resonance wavelength there are two possible modes in this structure that can propagate at different directions. So you can have a clockwise mode or a counterclockwise mode. They have the exact same frequency in ideal structure. So the idea is to couple those two degenerate modes at selective wavelength. So if we add a reflective element inside the ring, so the ideal ring doesn't have any reflective element inside it, but there are two modes that can propagate in contra-propagating directions. If we add a reflective element inside the ring, then we can get those two modes to couple to each other, and then from a ring we can get a reflection. So without this reflective element, we don't have any reflection. The light goes in, rotates there. But when you add this one, this mode that's coupled, and the input one will be coupled to the other mode, and we can get a reflection from the ring. So if we plot the reflectivity of this device, so the reflectivity is color-coded as a function of wavelength, and also the reflectivity of this small reflective element inside the ring. So the reflectivity goes from 0 to 1, and this is a function of wavelength, normalized to the free spectral range, which is the distance between two resonance wavelengths. And this is the amplitude of the reflectivity of this device. You can see at some, even at very small reflectivity amounts for these reflective elements inside the ring, we can get almost a reflectivity of 1 from the overall device. So the 1 is the red color there. So you can have very small reflectivity inside the ring, couple those two modes together, and get a very large reflectivity from the total device. More interesting than that, we can have a device here that has a selective reflectivity. So if we design a device here that has a reflectivity as a function of wavelengths looking like these dashed lines they've drawn here, then we can have reflectivity from the whole device only happening at one wavelength and have zeros at other wavelengths, at other resonance wavelengths of the ring. So we can get a single reflectivity from the ring. So ring resonators, as I mentioned, usually have equally spaced modes, but in this case we can select one of the modes and then get reflectivity at that specific mode. So for such a device with that selective spectrum, we can get a reflectivity of the total structure to look something like that. So we have a transmission, there's a main reflection peak, the blue lines, and at that reflection peak we have zero transmission, and we can have a very large reflectivity. So this is just a zoomed in view of that one. You can see that it looks very similar to what I proposed in the motivation section, that we can have a reflectivity peak without any side mounts. Something more interesting is if you consider a semiconductor laser that has a mirror which is wavelength dependent. So if you have a mirror with reflectivity which is a wavelength dependent or frequency dependent, then you can do a calculation and show that the line width of the whole laser will be reduced by a factor of Fc squared, which Fc depends on the slope of the phase of the reflectivity, and also the slope of the change in the amplitude of the reflectivity. So if instead of having just a normal mirror, like a cleaved facet, if you have a reflective element which its reflectivity is wavelength dependent, then we can get a reduction in the line width. If we calculate that reduction factor for our device, we can see that depending on where we set the wavelengths of the device, we can see a reduction in the line widths by a factor of around 150. So we also developed some design tools for designing these structures. The structure is very large compared to wavelengths. It's very hard to simulate the whole structure using full wave methods. So what we did with, as I mentioned, in the fast method for doing that, what we did, we developed a method that we can use to calculate resonance modes and use that resonance modes to calculate the reflectivity of the whole device using a perturbational method, looking at couple mode theory method. So the resonances can be found using 2D simulations because the device has cylindrical symmetry. The phi dependence is known because of that cylindrical symmetry. We can solve that two-dimensional problem and find the resonance wavelengths and the quality factor of that. Then we can use those modes that we found and expand the modes of a device with some perturbations added to that in terms of those original modes that we found. Just the only difference is that in this case the amplitudes are function of phi. And we can get a coupled mode formulation for that, which shows how does these two amplitudes are getting coupled when there is some perturbation added to the structure. Using that, we can do our design using this method. We use this method to simulate a 2D structure, just a toy problem. And we found that using a finite element method, there's the simulation results using that. And we use also our method to do that, and we compared the results. The results match very well between our simplified method and a full wave simulation, which is a discretization of the whole structure using finite element method. We used that design tools and fabricated these devices. We used silicon substrate, boron oxide as a lower cladding, silicon nitride, LPCVD silicon nitride as the core for these devices. LPCVD silicon nitride is known to have a low absorption loss at telecom wavelength, and that's why we use these material. So as I mentioned, we have a reflective element which is selective. In this case, it is it's a DBR written on the ring. So this is a fabricated device. When you zoom at that, it looks like something like that. So we wrote this using e-beam lithography. We etched it, and then we deposited the top cladding, cleaved the devices, and deposited AR coating and the facets, so that the reflectivity from the facet doesn't interfere with the reflectivity of the device itself. We can have also different designs. Another design looking like that improves increases the smallest size in the device and makes it possible to fabricate with full lithography. Also, for measuring these devices, we couple a tunable laser. We pass it through an optical isolator and a polarizer. We sample the light that goes to the device, and then we send the remaining light to the device. The transmitted light is the light is coupled to the device using tapered fibers, and we measure the transmitted light that goes through the device, Also, the reflected light is measured using a isolator, using a circulator. So the light that goes in, the reflected light goes to this detector. So we can measure the input, the transmitted light, and the reflected light at the same time, and then we scan the wavelengths, and we measure the reflectivity of the device and transmission of that at these single wavelengths. So we get reflectivity spectrum and transmission spectrum looking something like that. So the device was designed to have reflectivity at 1550 nanometer. We see a single peak with a very large reflectivity. There are some side peaks, very much smaller side peaks. That's because of the roughness in the fab. So the sidewall roughness causes the modes at this wavelengths to also couple to each other, but it's much smaller compared to the reflectivity at the design wavelengths. So also we measured that over 110 nanometer range, which was set by our laser, and over that whole range we had only one single reflectivity. If you zoom in at the main peaks look something like that. So for the reflection, it doesn't exactly look as what we expected. Also, the transmission looks fine. We figured out that this is due to the reflectivity that we get still from the facets, and there's interference between the reflectivity from the device and the facets. We modeled that, and so the solid line is the measured one. The model, which considers also the reflectivity from the facet, is the red dashed one. We did the fitting, and we extracted the reflectivity of the device. So if you plot the reflectivity of the device, in this case, this is the reflectivity and the transmission, or these dashed red lines. We can see that we get a single reflection peak. There's no side modes. The blue line here shows a conventional design of a DBR, which is for getting the same full width half max should be 4.3 millimeter long. So in summary, our device is 70 times smaller, has the same reflectivity, and it doesn't have these side modes. So that also has a faster roll off for the main peak. So just to summarize, I introduced the device today. These reflective devices, they can be useful for application in laser diodes. I presented some of the simulation methods that we developed for designing these devices, and presented and showed some of the characterization that showed that these devices can really be fabricated with the desired spectra. So thanks, and I'll be happy to answer any questions.
Question. Sure. Is there any advantage to coupling these microring resonators together? You talked about a single microring.
Right.
If you put 2 or 3, is there an advantage to that?
Yeah, there is an advantage, and people use them for making filters. So because a single ring resonator, as you saw, has periodic transmission depths. If you couple 2 different ring resonators with 2 different free spectral range, then you can get a single transmission depth. But the main problem is controlling the gap between those two and the amount of coupling.
Have you studied that at all, or?
No, not
yet.
yet.
Okay. I'm also curious, what sets the scale of the resonators, of the diameter of the rings, for example? You scale those down if you want to.
Right, you can scale them down, but there is a minimum radius that the light starts to radiate out. So the angle that the light gets reflected at should be larger than the total internal reflection angle. The smaller than that, it becomes small, and you get a radiation from the ring.
Everyone's been a long day so far.
What are the quality factors that you got from fabricating these microrings?
The quality factors were about, this one that I showed was 10 to 5, but we have increased them right now to 10 to 6. So we're improving the fabrication process.
And have you studied any thermal fluctuations in those devices? Are they sensitive to temperature or not?
They are. So the resonance wavelength moves by around 17 picometer per degree C. Also, on high Q devices, you will see thermal biastabilities at higher powers, like a milliwatts of powers, and that you will see thermal nonlinearity. So.
We're out of time, so let's thank Amir again.